Hello everyone. So in today's video I'm going to cover something related to prime numbers and prime factorization. Okay, so you might have heard of the Sieve algorithm and you might have heard about the prime numbers and how to find the prime factorization. But still is an important topic when I'm covering math related videos. I thought it would be good to cover such topics in a short video wherein I'll make you explain what is Sieve, how will you remember it easily, because when I was practicing for my DS, I could literally find it very hard to remember the Sieve's algorithm. And every time it was asked, I switch my tab and I search for the Sieve algorithm, and then I'll put that same code whenever it used to happen in any of the uh, contests or something like that. Okay, so better we could have an easy way to remember the Sieve algorithm and how can we approach that. Okay, so basically. Uh, our main question, first question, is to find all prime numbers from 1 to n. So let's say you will be given n in your as an input. So let's say thousands. From 1 to 1000, you need to find all the prime numbers. Now you might know what is the prime numbers, right? Prime numbers, basically, prime numbers have only two factors, 1 and n. 1 and itself, the number. Okay, whatever is the prime number, it has only two factors, 1 and its and the number itself. Okay, and the, I could say, number itself. Okay, then those are called the prime numbers, like 2, 3, 4, not 4, right? 5, 7, 11, and so on. So these are all the prime numbers. They do not have any factors other than 1 and those itself. 1 is neither prime nor composite. Okay, composite are the numbers who had factors, who had factors. Okay, now let's say what could be your naive approach for solving this question, wherein you need to find the all prime numbers from 1 to n. So what will you do? You will traverse from 1 to n and check whether I is prime or not. Now, how will you check whether the number I is prime or not? And how will you check that? So, basically, for checking the number as prime or not prime, you need to traverse until it's the square root of n. You need to traverse until it's square root of n and see if that number is a factor of I. That is, let's say that's j. So if I mod j is 0 or not, that you need to check. If I mod j is 0 or not, that you need to check. So let's say you have 15. So for 15, square root of 15 will give you what? Square root of 9 is 3 and 16 is 4. So square root of 15 will be 3 point something something. Okay, consider it 3.5. I'm not sure what is it, but let's consider it as 3 as 3.5. Okay, so then you need to traverse from 1 to 3 and check whether whether 15 is divisible by not 1. You actually start from 2. So whether 15 is divisible by 2 and whether 15 is divisible by 3, because always make it a note, always, or I could say, smallest prime factor of a number lies from 2 to square root of n. If the number is, if the number is composite, okay, then only it's if the number is composite, then only you will get any other prime factor than 1 and the number itself. Okay, so that's where I'm saying that your smallest prime factor always lie from 2 to square root of n. Okay, so here square root of n is 3.5, so you need to check for 2 and 3 whether 15 is divisible by 2. No. And whether 15 is divisible by 3, yes. So this 15 is not a prime number. This 15 is not a prime number, because you find some number from 2 to square root of n who which divides 15, I could say. Okay, so that means that 15 is not prime number. Okay, so I need to traverse until square root of n. So this will take my order of square root of n time complexity, and this will take my order of n time complexity. So in total, the time complexity is taken as order of n into square root of n, right? So at max you can traverse until 10 raised to 5 maximum. What would be the square root of 10 raised to 4 is 10 raised to 2, right? So yeah, you can traverse until 10 raised to 4 or 10 raised to 5, not more than that, I could say. Okay, because it's order of n into square root of n. And this is the naive approach. Okay, so is there any optimal approach for this? So that's where the concept of sieve algorithm comes. Sieve of Eratosthenes. Okay, so sieve algorithm is basically an optimal approach to find all prime numbers from 1 to n. Not just to find all the prime numbers, you can also find the smallest prime factor of a particular number, and also to find smallest prime factor of a particular number, because the algorithm is designed in such a way that you'll use a particular number and then you will mark all its multiples. You'll mark all its multiples as the non primes. Now, how is it? So, let's understand. Okay, let's say, how does this algorithm work? Let's say I have defined, um, consider this, you have maximum of n given as 1000 in this case. Okay, and you will make one prime array of size 1001. Okay, and you will assign as true. So that means all are prime numbers. I'm initially assigning as all are prime numbers. Now what the algorithm says is, you'll start from 2 and you'll go until square root of, you'll start from 2 and you'll go until square root of n. Okay, so let's say you'll start from I is equal to 2 and you will go the point where I square is less than equal to this maximum n, which is given as 1001 or 1000, and you will do I plus plus every time. Okay, now what you will check, if prime of I, that means if I is prime, so let's say initially I went to 2 and 2 is prime, right? Then of course 2, 4, and what else, 6, 8, 10, these all are multiples of 2, right? These all are multiples of 2. So those all can never be prime because those are multiples of 2 anyways. Okay, so 2 being their smallest prime factor for all these numbers, this all can never be prime, so these all are non-prime, so we'll mark their prime of that particular j's as false. Okay, now when you came to 3, you'll not start from 6. No, because for 6 it's always 2 as the smallest prime factor. For the particular number I, will always start from I square, because I square is the next number whose smallest prime factor is square root of I. And that's where we found that we have to check until square root of n. Now, if you realized, and here also we are going until square root of n only. Okay, so what is my algorithm? If I have a prime of I, then I'll go for j is equal to, I'll start from I square until it's less than equal to n, and every time I do plus equal to I. So let's say 4 and then plus equal to 2, 6 plus equal to 2, 8, because this is multiple of I. 9 plus equal to 3, 12, right? Plus equal to 3, 15, and just like that. Because then that's a multiple of I you have to take. And now what you will check? If prime of j, or is it needed to check? No, no need of checking. This j is always non-prime. So I'll make prime of j as what? False. That means j is not prime. And you got. So whatever are true marked now, those are your prime numbers. Okay. True marked are prime numbers. So this you can pre-compute anyways with the maximum n given in your constraints, and then you can use this prime numbers in whatever question it's given to you while solving the question. So in this way, your time complexity has reduced until what? Now what you have to do, you just have to make a vector. Let's say you need to return all these numbers from 1 to n which are prime. Okay, then what you will do, you'll start from 2, you'll go until this maximum of n. If you have this prime, then you will push back those I in your answer vector. That's it. And then you will return the answer. Okay, so this way you will get all the prime numbers from 1 to n. Okay, and the time complexity will be, your time complexity is order of n into log of n. Order of n into log n, right? And space complexity again will be order of n only. Okay, now have you realized that this time when I'm making it false, if it is not already false and I'm making it false, basically that's the smallest prime factor I'm getting. Okay, so what if you need to find the smallest prime factor? So this is for finding all the prime numbers. Now what if my another question is, find all prime factors of n, of number n. So let's say if it's 10, then all the prime factors of n are 2 and 5. Okay, for 15 it's 3 and 5. Okay, for 20 it's 2 into 2 into 5. So basically it's 2 and 5, all the prime factors. Okay, it's 2 into 2 into 5 or 2 and 5. So this way you need to find the prime factors of n, or you need to just find the factors of n. Let's say factors of n, then also this will come. Okay, you will find the factors as prime only. You will not find any composite factors. Never. If at all you will be asked to find the factors of any number, you will write it in the form of prime numbers only, the multiplication of prime numbers only. If at all it's 100 also, then also 2 into 2 into 5 it will be, right? And this way you will write the factors of any number n. Now what if you need to find the factors of any number n? How you will do it if you have to find it? Then let's say if I find the smallest prime factor of each number, smallest prime factor of each number, let's say if I find the smallest prime number of each number as SPF of n. So SPF of n is smallest prime factor of number. So for 10 it's 2, for 15 it's 3, for 20 and 100 it's again 2. Okay, for 49 it's 7, and that way, so on. Okay, so you could see the smallest prime factor for each number. You could find the smallest prime factor of each number using Sieve algorithm. You can find it using Sieve. Now while doing Sieve, what you can do, rather than making prime, I could make an SPF array of size n, maximum n, some maximum n. Okay, I could make this array, and this is initialized to 1. So initially the smallest prime factor of each number is 1. Okay, anyways 1 is there. Now what I could do, I could traverse from 2 until I less than equal to this n, maximum of n, because for every number I have to find the smallest prime factor. Okay, so for every number I need to find the smallest prime factor. Now what you could do, if again smallest prime factor of I is 1, that means I is prime number. So if the particular number is prime, you will start from j is equal to I. Okay, here you could start from I square also, basically, but and that also won't affect it. You can start from j is equal to I square also. Okay, you can start from j is equal to I square, j less than equal to this maximum n, and every time j plus equal to I. If now you need to check if SPF of j is 1, then only you will make its SPF as I. SPF of j as I, because I will be the smallest prime factor for that. Now let's say for 2, you have marked the SPF of 4 as 2, 6 is 2, 8 is 2, 10 is 2, 12 is 2. Now, when you come to 3, you'll start from 9. So, for 9, it's 3, smallest prime factor. Okay. Now, 9 plus 12. But 12's prime factor is already 2, so you will not mark it as 3. No. 12 is 2 into 2 into 3. Right. So, smallest prime factor is again what? 2. It's not 3. So, you will not mark it. You will not mark it. Correct? You will not mark it. So, this way you will get the smallest prime factor of each number. And now, if you want to find the prime factors, so find prime factors. So every time what you will do, let's say I've got the smallest prime factor of 12 is 2. Then I'll so my one factor is 2. Now again 12 divided by 2 is 6. So I need to find the smallest prime factor of 6. 6 is again 2. Okay. 6 divided by 2 is 3. Smallest prime factor of 3 is 3 only. So this is my factors of 12. These are my factors of 12. So how you will get the prime factors now? You will have a vector of int something called as get factors for number x, let's say. Okay. And you will have that answer array over here, while your x is not equal to 1. So then 3 by 3 is at the last step, 3 by 3 is 1. So now no need of it. So until your x is not equal to 1, every time your SPF of x is your answer, is your one of the factor. So in answer, you will push back what? SPF of x. And this SPF you have pre-computed. This pre-computed. It will take SPF, finding SPF will take order of n into log of log n time complexity, as we have seen. For the sieve, same like sieve. So you'll push back SPF of n under that, and you will divide your x by SPF of x. Sorry, this could be x, not n. Okay. And your answer will be your final answer. And that will be all the prime factors for all the factors of x number. So this overall will take, you will divide. So let's say if the smallest prime factor is 2 only. So for 8, it's 8 divided by 2 is 2, cross 2, cross 2, it's 2 cube. So basically 3 factors. So 3 times you have to run this loop. So it's basically log of 8 times. You could see. Okay. So the time complexity of getting factors is order of log n now. If pre-computing of SPF has been already done, then it will be order of log of n. I hope you're clear with this. So these are the basically two main algorithms which you can compute using Sieve. One is the getting all the prime numbers from 1 to n. Okay. And second is finding the smallest prime factor and then using that get all the factors of the particular number. By using these two algorithms, there are so many questions wherein you will need the use case of getting all the prime numbers, getting the smallest prime factor, getting all the factors of particular number. So these two algorithms would hit that in the optimal time complexity as you can. Okay. So in the next video, I'll be covering some of the questions related to this algorithms. You'll actually get the hands-on on how to use these algorithms, on what type of questions it will be used, and so on. So stay tuned for the next video. Do share it with your friends, like, share, and subscribe. Stay tuned, stay safe. Bye bye.